Welcome to this video lecture on row equivalence. As I mentioned in class, I apologize I'm not there in person, but hopefully the sound of my voice and the mathematics involved will satisfy you, at least for this one go. Recall, what are we trying to do? We're seeking to solve systems of linear equations systematically and to find all or no solutions. So as we go through, I'll be providing some examples, and I'll also be providing some exercises where I hope you can fill in the details before I either discuss the solution, so you can pause the video, or I actually present some work solutions. I encourage you to give it a go before continuing. I'll give you a warning when they come up. So from our system of equations, last time, you recall that we obtained the augmented matrix. Which we wrote A with this vertical slash B. And today, we're going to study what's known as row equivalent matrices. Where secretly any matrix that we deal with today will actually be this A/B augmented matrix. So just bear in mind that our goal today is still to continue trying to solve systems of linear equations. So let me give you a statement of what it means for two matrices to be row equivalent. So two matrices are said to be row equivalent if one can be changed into another using what's known as using a sequence of elementary row operations. So what does this mean? We're going to shortly define what elementary row operations are, but the real meaning behind these operations is that the solution space to our systems of linear equations remain the same. So solution space just means the solution set, what values actually solve our system of linear equations, and it stays the same. So if we consider again the example from last time, sorry, just to mention that this statement here started here and ended here. and we'll explain what elementary row operations are very soon. So consider the example from last time where we had 5, 7, 4, 5, the matrix, this 2 by 2 matrix applied to xy to give 13, 10. And if you remember, we did manage to solve this. We used invertible matrices. Last time we saw that this was an invertible matrix, and we applied the inverse on both sides, so here and here, to actually compute what the solutions are. But we're not going to worry too much about that today. But what we're going to observe today is that I could change some of these equations and still keep the same solutions. So for instance, as a simple way, this is like we do in high school. If, say, I added this equation and this equation, I'm going to keep the same solution set, provided I keep one of the other ones. So let's say we replace the second one. I still have 5x plus 7y equals 13, but I replace this starting equation with 9x plus 12y equals 23. But you can see, just like you knew from high school, the solution set remains the same. But in the terms of today's lecture, what we actually see is that the augmented matrices would be row equivalent. So what, again, are those augmented matrices in this case? Remember, in this first case, we had 5, 7, 4, 5, straight line, 13, 10. And in the second case, we had 5, 7, 9, 12, slash 13, 23. So these two matrices are row equivalent. And that's the theme we're going to do today. So just before moving on to the next page, let me just read again the statement, and we're going to continue with the definition of elementary row operations. Two matrices are said to be row equivalent if one can be changed into another using a sequence of elementary row operations. In the example here, it was just adding the second one to the first one. Okay, I'm going to move on to the next page. If it helps, you should be looking along with the PDF. Maybe that makes the jumping a little bit easier to read. So just as a notation, for simplicity, we're going to write So we write row I, the Greek letter rho, for, well, row I. I mean, the only reason we use this letter is that it just sounds the same. And then an elementary row operation is one of the three following operations. So we have the first one, which is multiply the row by a non-zero number. So by a non-zero scalar. If you prefer the mathematical notation, we can say that row I becomes lambda times rho I, where lambda is some non-zero scalar. The second option, which we saw earlier, is that we can add one row to another. In this case, for instance, rho I could become rho I plus rho j. And the third is to interchange two rows. Swap them. So if I just go up to my example beforehand, just in words, we can see if we start off with two systems of equations, if I multiply both sides by some number that doesn't change the solutions, I can add one row to another to replace it. That doesn't change the solutions. Or I could just rewrite them in a different order. That certainly doesn't change the solutions of this system of equations. So everything that we've done is designed to keep the same solution set, and it's also designed to be invertible. I can go back and forth. So make an observation here. All three types of elementary row operation, and I'm just going to write ERO, are invertible. So that means you can, for instance, if I multiply by 5, I can go back by dividing by 5. And the observation is that because this is the case, if A and B are row equivalent, then B and A are row equivalent as well. You can go the other way. As a note, just as a remark, you're only supposed to perform one elementary row operation at a time, but there are some standard combinations. And the example that's important to know is you could multiply row j by -1 and then add it to row I. This has a different name. I'm sure you can guess what it is. That's the same thing. Subtracting row j from row I. Okay. And you can probably come up with some other ones of your own. So just so that this doesn't get too theoretical, let's do a concrete example. We're going to show that two different matrices are row equivalent. Just as a remark, whenever you're doing these row operations, please be helpful and actually write down which operations you're going to do. So you notice that when I do this, I'm going to be very careful in writing down each time which operations I'm doing. So let's start with 3301,110. I'm going to multiply the first row by 1/3. And you notice that I write down what I'm doing. Particularly when you're being assessed on this, I can't stress how important this aspect is. The person grading your work will have no idea what to do if you don't tell them what you're doing. And this applies beyond this. Whenever you're giving a proof or some argument, you should try to be as specific. You don't have to be wordy, but you have to be specific as to what you're doing. Okay, so when I multiply the first row by 1/3, I just get 1, 1 on the top, and nothing else happens for the lower rows. And then I use my combo from above to subtract row 1 from row 3. So this was my combo of subtracting row j from row I. So row 1 doesn't change. You notice that as I write them, often nothing will happen to some of the rows. But row 3 becomes this, subtract that, and I actually get 0, 0. And lastly, I'm going to subtract row 2 from row 1. So I get 1, 0, 0, 1, 0, 0. I subtract off that 0, 1 from this 1, 1. Okay, good. And that was what we wanted to do. So here's your first exercise of today. Just to check you're watching along with the video. I want to ask you, is this matrix row equivalent to this other one I'm going to write down? And if yes, why? So find a sequence of elementary row operations exhibiting this equivalence. And if no, why not? So I'll let you think about this. So at the beginning of next lecture, we can talk about this. I want you to think about it first. For the following exercise that you're going to go see later, I will provide a solution. So this might be a good time to take a little break. We're going to move on to actually using row operations to solve linear equations, using the same example as from last time, but maybe you want to take a minute, get a cup of tea, bit of chocolate, sandwich, burger. Okay, so we're back. So we're going to use row operations to solve linear equations. This was our whole point. And we're going to do it in the case where we already know the answer. So from last time, if you get your notes, you'll have seen that we did this already. We saw that we started off with a system and this was equivalent to the matrix form. And that was equivalent to the augmented matrix. So the way that we use row operations is to basically do what you did in high school, but we're going to keep track of row operations. So the idea is that we're going to cancel out the x variable. You could cancel the y variable as well, so there's some choice. But we're going to cancel the x variable. And what we're going to do, we're going to multiply the first row by 4 in the augmented matrix. And we're going to multiply the second row by 5. So that's going to cancel out the x variable when I subtract. More succinctly, we're going to do this in terms of row operations. So I said earlier that you're only supposed to do one row operation at a time, but you see that I'm already starting to cheat a little bit when you get familiar with this. So applying this to the augmented matrix, I get so there's some arithmetic here. Hopefully you're doing this along with the video. Maybe you can even go ahead and see what should happen. So here's the cancellation part. So row 2 becomes row 2 minus row 1. This was the combo. So nothing happens to the first row. The second one kills that x term, so I get a 0. And so as a remark, at this stage you might just try back substitution, but we're going to proceed. Back substitution, where this works out what y is, you plug it back into the equation and you work out what x is. But we're going to try and read off the solution. And so instead of explaining each row again in such detail, let me just tell you what happens and do the computations. We're going to, this time we're going to try and kill off this term so that we actually have an evaluation of what x equals and what y equals. So we're going to get row 1 becomes minus 3 row 1, and row 2 becomes 28 row 2. So the numbers are getting a little bit hairy. And now we're going to subtract row 2 from row 1 to get and finally we're going to rescale, so we're going to kill off this term by dividing through by minus 60 and kill off this term by dividing through by minus 84. So this time we're going to rescale to obtain row 1 becomes 1 over minus 60 row 1, and row 2 becomes 1 over minus 84 row 2, and this gives me 1, 0, 0, 1. So there's the identity matrix, you might notice. 5 over 3 and 2 over 3. And hopefully, fingers crossed, we got the same solutions as before. This augmented matrix says exactly the same. It corresponds to x plus 0y equals 5 over 3, and 0x plus 1y equals 2 over 3. So there's the solution we got from last time. Okay, so one more quick break for you, and we got one page to go. We're going to talk about matrices in echelon form. So this is just a definition to get you going with the next lecture, where we're going to do much more on this. So let me give you a sketch. A matrix is in echelon form if it looks like, well, it looks something like, well, there are bunches of zeros, and then there's this staircase. Maybe there are lots of them. And then here there's a non-zero term, and then there's possibly zero, but arbitrary values. So here we have zeros. We're allowed to have rows of zeros at the bottom, but we don't have to have very many. So a simple example might be some matrix. Here's a big matrix. It looks like 0, 1, 3, 0, 7, lots of zeros, and a non-zero term, and then some more zeros. We can have as many rows as we like. And I like to draw this, what I call the staircase. And notice here there are what's known as some leading entries. Those are the stars. And a leading entries, what properties does it have? It's the first entry in each row. That's non-zero. And it's to the right of the previous leading entry. So the previous would be a higher up. So the final exercise, and I thank you for listening along to this lecture. Put the following matrix into echelon form using elementary row operations. And we're going to do 0, 1, 1, 2, 3, 4, 0, 1, 0. And again, you should pause the video now, try it, or get a cup of tea, take a quick break, come back, and I'm just about to show you the solution now. In fact, it's very quick. So when you swap the row 1 and row 2, notice that I'm looking for this kind of staircase format. So I want the top left one to be non-zero as far as I can get it. So this is equivalent to 2, 3, 4, 0, 1, 1, 0, 1, 0. And that's equivalent to, once I subtract row 2 from row 3, so nothing happens up here, nothing happens here, but I'm going to subtract row 2 from row 3. And notice that what do I get? I get a staircase, and I have some leading terms. And that's it. So today we covered row operations, how they can be used to solve linear equations, and this slightly different bit at the end where we introduced matrices in echelon form, and we used row operations to convert some starting matrix, which could be arbitrary, into something of a more systematic format. We're going to continue with this idea next week. We're going to study what's known as reduced echelon form. So it's even more systematic. And we're going to introduce what's known as Gauss and a separate thing. Sorry, the first one being Gaussian. Apologies. Gauss-Jordan elimination.